Hello, everybody. It's good to be here. First of all, I would thank the organization for this amazing event that you're organizing. And my name is Filipe Mulonde. I am originally from Angola. It's a country in sub-Saharan Africa. I have a bachelor degree in software engineering, a master degree in applied mathematics and computer science from St. Petersburg Polytechnic in Russia. I'm doing research at ETH, where I work since September of last year. I started working with SAFAR usage group, and SAFAR stands for Safe, Fair, Robust, and Intelligent Computer Architecture. And we are a part of the Department of Information Technology and Electrical Engineering at ETH. And the SAFAR research group, we do research across the entire stack of computer systems. We do research in memories, processors, and hardware, software co-design. We build accelerators, and also we work in emerging workloads such as bioinformatics. The SAFAR research group is led by Professor Dr. Onur Mutlu. And Dr. Onur Mutlu has a YouTube channel where you can find a lot of resources about computing system, how to design them, and what are the key trends like latency, bottlenecks, and problems in modern computing systems, and also solution on how to overcome them. My talk, foundation of DRAM, latencies and bottlenecks. We will talk about two components of some embedded systems, the DRAM, as a commodity DRAM itself, and also we will talk about some problems that DRAM shares with embedded DRAM memories that most of the time I use as buffers in some accelerators or last level caches in other accelerators also. So this is the outline of my talk. There is, I think, a little bit to cover. I will be a little bit fast sometimes, so bear with me. So we start with, the motivation for this talk is that today we are in research. This is what we are trying to achieve. We want fundamentally secure, reliable, and safe architectures. We want fundamental energy efficient architectures, and we want fundamental low latency architecture. But unfortunately, with current state-of-the-art DRAM, we cannot achieve none of this. It's almost impossible to achieve that with the state-of-the-art DRAM. You can take even DDR5, for example. It's impossible to achieve all of this. None of them we can achieve with this state-of-the-art DRAM technology. And emerging workloads such as machine learning, genomics, medicines, and health, they require this in order to work, to be enabled efficiently. At ETH, I do research on bioinformatics and DRAM itself. I try to design architectures and also softwares or algorithms for genome analysis. And genome analysis requires a lot of data. And it is highly important because with this, we can enable precise medicine. For example, this is an example of DNA of various people. And just by looking at some position of the DNA, we can detect if a particular person is more prone to develop certain kind of disease. So this is highly important in able to provide precise medicines, especially for infants, because when they are born, they only cry, and the doctors don't know what they have. So it's important to sequence the DNA to look at particular SNPs so that we can potentially find out which kind of medicine we can enable them. And we need to find it as quick as possible because many infants don't have, for example, even 10 hours sometimes because of some disease that may have. So you need really this quick as fast as possible. This is a particular example of what is already possible to do today. By looking at a particular position of the DNA of a person, you can look at particular genotypes. And based on the genotypes that you find at the particular loci in the DNA of the person, you can, for example, provide which medication for hepatitis C is most suitable for this person. I work with variant calling a lot, and I can tell you, for example, it takes a lot. Even like the last experience that I did, I was using, I think, 256 threads, and it was taking more than, I think, 7 to 8 hours just in a single chromosome with a coverage of 20. Even for emerging technologies also, like edge computing, you can see to enable the applications, the tier 3, we need the components or catalysts in the tier 2 to be low latency and provide high bandwidth. So what's the goal of this talk? The goal of this talk is to understand how DRAM memory works, to understand the latencies and bottlenecks and how decisions made in hardware affect the software and the programmer, to understand the importance of making design and optimization decisions that cross the boundaries of different layers and systems components. Let me just put my clock so that I know where I am. So let's go to the background. So the background, we want to provide understanding of commodity DRAM. So in the first point, we have a processor, and the processor we have cores. And inside of this core, we have a memory controller. The memory controller is a component that is embedded in the CPU itself. And in the past, it used to be a different chip, but today mostly embedded in most systems. So the memory controller receives requests from different cores, and it has the task to convert these requests into commands, because the DRAM itself doesn't understand requests. So the memory controller needs to convert requests to commands. The memory controller needs to buffer requests coming from different cores. And the memory controller also needs to schedule these commands to the DRAM model itself. And the memory controller and the CPU itself is connected to a DRAM model using a memory channel. And the memory channel is composed with multiple ranks. And the ranks is basically a set of DRAM chips. And inside of DRAM chips, what we found is a bank. And inside of each bank, what we have are subarrays. And inside of a subarray, what we have is a mat. A mat is basically a 2D arrays where a row of cells share the same word line, and a column of cells share the same bit line, and a row of cells are connected to a row decoder, and the column of the studio arrays are connected to a row buffer, and the set of these row buffers is what is called a row buffer. Is what is called a row buffer, because these single components called sense amplifiers, and the set of them is called a row buffer. I know how many people have heard about cache misses, cache hit. Who here have heard about row buffer hit, row buffer miss? How many? Okay, it's good here. So we can move forward. So it's a deep look at the DRAM bit cell itself. Well, every cell is connected to a word line, and they're also connected to a bit line, also connected to a sense amplifier. Inside of the cell itself, what we have is an access transistor and a capacitor. And then the word line enables the access transistor so that the capacitor inside of the cell can share charge with the bit line. Going forward, we will understand more about this mechanism. And inside of a DRAM mat, what we have is a collection of cells, and each row in these 2D arrays are connected to a local word line, and then we have the sense amplifier and the column select lines. Basically, when a memory controller is issuing to want to access some region in DRAM, it must provide the bank ID and also the columns of the particular row that it needs to access. So this select marks is used to select which of these columns for a particular row we want to access. And then a collection of mats itself, they make a composition of a subarray. And a collection of subarrays, they make up a DRAM bank. In a DRAM bank, a subarray shares certain components. For example, we have the row address, we have the column decoder, the global buffer. So basically, a row address partially, when it receives a command from the memory controller, for example, to activate a particular row, it decodes the row partially, and then send this partially decoded row to multiple subarrays, and along with a signal that specifies which subarray should be enabled, and then we access the particular subarray. Inside of this particular says a collection of maths access through the local word lines, a particular row is activated. And then we, using the column decoder, we decode which column in all of these maths we need to access a particular cell. It's a lot to cover about DRAM. It's really, the hierarchy is really a little big, so you need to go through many details, but unfortunately we don't have too much time. And this is how a DRAM chips look like. We have a lot of banks, and this bank shares a data buffer together. And as we saw before, a collection of chips make up a DRAM rank, and this DRAM rank, normally they share the same command bus. So they work in a lockstep manner, a collection of chips. So now let's try to understand the life cycle, for example, of a DRAM read or a DRAM write. So in the point number 1, what we have is a DRAM bank or a DRAM math in a pre-charge step. The pre-charge step is a state where we are able to access a particular row. So in this state, the bit lines that share with the sense amplifier are placed with voltage by the maximum voltage of the array divided by 2. And this is what allow the sense amplifiers to read a particular, to work effectively. So after the memory controller sends an activate command of the process that I described prior, a particular row in a particular subarray will be enabled or asserted. After that, the access transistor will be enabled, and because of that, the capacitor inside of the cell will discharge or charge depending on the value that you have in the capacitor itself. And there will be charge sharing between the capacitor and the bit line itself. And depending on if it was charged or discharged, the sense amplifier that is connected with the bit line will be able to amplify the value that was sensed. For example, in this case, since the capacitor was full, there is a small charge sharing between the capacitor and the bit line. So we have a disturbance in the bit line. It's no longer VDD divided by 2. Now it's VDD divided by 2 plus some delta, meaning the charge that came off the capacitor. The sense amplifier is able to sense that, and it may detect that this is a 1. Since activating a particular row destroy the value of the capacitor itself, the next step in this pipeline is the sense amplifier needs to amplify the value based on what he was sensing in the bit line. So it's enable it to effectively restore the value of the cell itself. After some time, and the memory controller to issue different commands, you need to respect timing parameters. It's not only you need to send one parameter and then the next one. There are timing parameters that need to be respected. So for example, from the activate to the read, the timing parameter that needs to be respected is the TRCD. It's corresponding to a number of cycles or a number of nanoseconds that needs to be waited before we send a read command. So after TRCD, the memory controller can send a read command. And when we send a read command, the data can be able to is in the sense amplifier, and then we can transfer the data through the I/O of the bank. After that, we need to prepare the DRAM bank for a next read, possibly in a different row. So in this case, we need to send a pre-charge command. What the pre-charge command will do, it will deassert the row, and we put the bit line again in a VDD divided by 2, so that the sense amplifier can be able to sense again data from a different row. After some time, the pre-charge command, after the pre-charge command, the cells, the bank is ready for a next command, such as activate. So from the activate command to the pre-charge, we need to respect a TRS command. And from the pre-charge, from the pre-charge again, there is a TRP after pre-charge that we need to respect before issuing a next activate command. But the memory controller is in the CPU and is mostly the head of the DRAM itself. The DRAM, let's say, it's dumb because it relies completely in the memory controller. It's a memory controller need to respect your timing parameter because if you don't respect that, you will have values that you will not work properly, and I cannot assure that you will be able to work correctly, or the system will not be able to work correctly. So the memory controller needs to have a lot of work to do. So the memory controller needed to schedule commands in order to prioritize some demands, for example. It can try to prioritize, for example, bank level parallelism. It can try to prioritize also, for example, hit, for example, in the row buffer. Why? Because when you see the process of activating a row is too expensive. And if the next command that you have if you have commands in your buffer in the memory controller that's going to the same row, you don't want to close that row and then do all of that process again. So you want to prioritize and look for commands that are going to the same row. But it's end up becoming highly complex because it's end up provoking some denial of service, for example. And there is research showing, for example, when you provide read, some applications work poorly. Because think about you have two applications in your system. One is streaming, meaning it's accessing consecutive location in the same row. So this application will always be prioritized than the other application that is accessing random locations in your DRAM system. So you end up having problem of fairness. So it's important to the memory control to be aware of that also. So and from this graph, we can see that hits, for example, if you hit, you can save a lot of energy, for example. If you miss, you also can it's expensive because you need to activate a different row. You need to activate a different row and then present the read. But if you have conflict, it means like you need to close a row. After close a row, you need to open another one and go forward. So conflict is the most expensive. It's basically what you don't have. Miss is less expensive, but what you really want all the time is a hit in the row buffer. So these are pictures of how the memory controller translates the address. For example, we saw the structure of a DRAM. So we saw that there is rows, there is channel, there is rank, there is bank, there is column, and there is chip. All of these information comes in a memory address. And here we have some types of scheduling technique that the memory controller can use in order to schedule commands. So let's now talk about latencies and bottlenecks in memory systems. So this is a study done in 2015 by Google. They analyzed all the workloads that they have in the servers, and they found that the majority of these workloads are memory bound. So they are backend bound, and when you go a little bit, because it is a top-down profiling approach, you can see that the majority of cycles are stalled because of caches. Another work also shows that 62.7% of the total system energy spent on data movement. So basically moving data from the DRAM to the entire memory hierarchy to the register in your CPUs. And it's also clear when you look at a modern CPU, for example, you can see that the majority of components that in a particular CPU today, in a modern CPU, is dedicated to store and moving data. You can see the computation units are very small. They have these red lines. There are particular cores. But when you go inside of the cores itself, what you still have cache L1, you still have buffers, you still have the register files, and you still have a lot of tables that basically are using for heuristic in a particular processor. So you can see here that how modern CPU is evolving today is mostly about how to move and store data effectively, a good part of the job today. But let's take a look at the latencies. We talked about these DRAM timing parameters that the memory controller needs to respect. Here are some numbers for DDR3, for example. When you send an activate and then you send a read, you need to wait 50 nanoseconds, and then you activate to read 50 nanoseconds. The same for write. Activate and then a pre-charge is 37 nanoseconds, and so on. This is for DDR3. But for modern DRAM technology, it's almost the same, or even worse if you go to DDR4 or DDR5. So it's not really getting better. This is data showing how DRAM is being evolved over the years. We see we have like 128 in terms of capacity. We have 20 in terms of bandwidth, but 1.3 in terms of latency. So DRAM people are not really working to increase latency. It's almost about capacity today. So things are really not getting better in terms of latency. So we have some commands also, how the untiming parameters, how they have been evolving. Here, basically we have activation, pre-charge, restoration. And the question that we also need to ask ourselves is, why the memory latencies? The reason number one is the design of DRAM microarchitecture is to maximize capacity area, not to minimize latency. The second reason is like the design of most DRAM chips today is one size fits all. Why? Because it's very hard to process, at least to get like less errors, how I can put it together. So when you manufacture DRAM, some cells will not work. So in order to make every cell, to work in a certain operation condition, you need to have almost place your latencies to the point where even the weakest cell that you have there will be able to work effectively. Because basically we don't want to throw away this DRAM chip because it's costly to manufacture and then you keep throwing away. Because it's really hard to manufacture DRAM chips without errors. So what we have today is one size fits all. So some latency parameters for all temperatures, some latency parameters for all DRAM chips, some latency parameters for all parts of the DRAM chips, and some latency parameters for all supply voltage level, and some latency parameters for application data. So basically, if you look also in the research in DRAM today, you see that there's a lot of work and people trying to speed up DRAM by using this. Oh, we have 10 minutes. Okay, so we try to go really fast. So DRAM refresh is one of the main bottlenecks that we have in the memory system today. So basically, even if you're not accessing any data in your system, your DRAM cells need to be activated and pre-charged. Why? Because the capacitor inside of your DRAM cell leaks. So every 64 nanoseconds, even in some modern system is actually 32, you need to refresh your DRAM cells. So this is the research overhead, for example. In a 4 GB chip, for example, 80% of the time you spend on refreshing, and 46% we spend in a 64 GB DRAM memory. So when a particular DRAM bank is being refreshed, you cannot access it. So basically, the memory console needs to stall request to prioritize refresh, otherwise you lose data in your role. So the same almost for, we also have data for energy, for example. 4 GB is 50% of your energy, and 64 GB, it costs you 47% of your energy consumptions just going to refresh. Not accessing, not perform any computation that you're doing, just basically refreshing yourself. So there is many technologies that have been used to solve this problem, but I don't have much time, so we go a bit faster. So we have actually many problems in DRAM. How many people knows about programmer? Okay, this is good. So the programmer was actually presented to the world by the Sapphire Research Group. And we skip it a bit. Okay, so we talk about how we know that this DRAM is slow. So what we can do and what we've been seeing, for example, in some accelerators, for example, is what people, I'll use this example, for example, these people were trying to build an accelerator for machine learning, for example. The main problem was that these buffers were small, and because of that, a lot of requests need to go off the chip. So some solution what some people use in some system is to replace this buffer that normally are SRAM with eDRAM, basically embedded DRAM, because embedded DRAM can provide much capacity. But the problem of embedded DRAM is that embedded DRAM have a capacitor inside of the cell, meaning you need to refresh. So then how do you overcome this refresh overhead? And these people actually have done some study, and in gray is the amount of time this particular accelerator spends just on refreshing, for example, the energy percentage that goes just by refreshing. So some of the techniques that we use in some application is basically to violate timing parameters. If you violate the timing parameters of the DRAM standard, the standard say, I cannot assume that your chip will work reliable. So basically what we have is errors in your data. Some bit, some cell that 1 becomes 0. So on this timing parameter violation can be done at many levels. You can violate, for example, the activate or the TRCD, for example, timing parameters. You can violate the TRP. You can violate any timing parameters you wish. But it's not only about violating timing parameters, right? You really want to understand if the downstream workload that you have in your system is resilient to these errors that can come of your memory system. If you look at machine learning or deep learning, for example, they are very resilient to this error. And many people have designing some accelerator and proposals actually to get speed or power, because you also can reduce the RI voltage in your DRAM. But if you reduce the RI voltage in DRAM, you need to adjust your timing parameter. You need to become even slower. But you can say, okay, I will reduce the power. I will not adjust the timing parameters. And the errors that will come out, my workloads can still work effectively. Because, for example, I have a neural network, and it's resilient for this kind of errors. So this is what many people, some people have done, and it highlights the importance of think widely when designing and optimizing a system. So basically, if you know the problem that you have, you know the algorithm that you have, you can leverage the properties that are downstream in the entire stack. For example, if you know that you have a neural network and it's resilient to errors, and you want to use less power or even want to increase your speed up, you know that if you violate the timing parameters of the DRAM, you can get speed, you can reduce power, and your application may still work correctly. So this is the idea of violating timing parameters, for example, to overcome some latencies and bottlenecks that we have in commodity DRAM. So basically, this is what these people was doing this paper did, and they only did for refresh parameter. But you can see that one of the key ideas that they use, okay, we need to train our neural network under these errors itself. So basically, you have data in your DRAM. So basically, even in the training process, you insert some arrows in your data. It looks like some data augmentation now. So that you know where your neural network will be deployed, this arrow will be there, and you need the exact arrow model of your DRAM because different things that you play with have different arrow model. We know, for example, for refresh, it's almost random across different DRAM banks. So every cell have almost the same probability of experiment, a bit flip, if you reduce the refresh, if you increase the refresh interval. So people use this arrow model and they apply it to their application so that they can make the workload more resilient. And this is another paper from my group. In this paper, we actually play with the voltage and also with all the timing parameters of the DRAM. And this is the amount of power that we can save across different neural networks, for example. Yeah. Okay, so I'm open to any question. We needed to. Yeah.
Check. Yeah. Thank you for the question. Great talk. Great talk. Do you have any questions? Yeah, over there.
Just for clarification, you said that the DRAM refresh percentage increases, but isn't the DRAM only locking one row for the refresh?
No.
So the other rows are accessible? No.
So basically, every row must be accessed. Like if every row, the DRAM itself for the memory controller is basically not aware which DRAM bank, which DRAM row have your data. So you need to refresh after 60 milliseconds on every row. And this refresh is done in two ways. Sometimes the entire module is not available to you because all banks are being refreshed. But some new technology today, they provide what's called per bank DRAM refresh. Basically what you can do, you can refresh one bank and you can still access other banks, for example. But in the end, every row in the DRAM must be refreshed, otherwise you lose your data.
But the impact for the application should be reduced, isn't it?
Your application, can you repeat?
If you only lock one bank for refresh,
yeah,
then you can still work and you're not blocking the whole CPU with 8 cores, because some cores might access banks that are not currently refreshing.
Yeah, it really depends a lot on your DRAM, in your mapping, right? How you map your data. Likely, you don't want, let's say, 60% of your data access going to the same bank, right? Because if this bank is being refreshed, then you need to wait. So the memory controller needs to be smart enough to parallelize this so that it can schedule and prioritize requests that goes to different banks because he knows that the different bank is being refreshed, for example. It really depends on your data mapping. And there is also a lot of research on how to map your data effectively. Even most of the work that try to, even to explore this resilience, they also try to really do that.
Thank you.
Any other questions over there?
Good morning. Have you studied the trade-offs between adding error correction schemes such as ECC, which need more energy, versus having an underlying system that requires less energy, so that maybe your error correction scheme can prevent your application from experiencing the errors due to the lower power that you provide to the memory system?
This is a good question. For the top of my knowledge, I think like most of chips today with ECC, they are able to detect one error per word, and they can correct it correctly. If you have two, they can detect basically that, okay, there is a fault. It will not correct it, but can detect and say, okay, this is fault. But if you have more than that in a single word, your error corrector cannot even report anymore. So basically, if you use ECCs, you can definitely have some help. But ECC also complicates a lot. There is some papers and some research, especially in my group, that shows, for example, because if you want sometimes to exploit this resilience, basically what you want to do, you want to profile. So you want to profile, basically. Basically what you want to do is, you want to find weak cells. And people actually have profiled the DRAM chip itself, and they find out like only a teeny small set of cells actually need to be refreshed at 64 and to 128 milliseconds. Most of the DRAM cells can actually be refreshed more than 256 milliseconds, and some of them, again, 128 to 256. So if you know this, what you can do? Well, you can basically bin, right, some of these cells in the memory controller and say, this set of cells need to be refreshed at every 64 milliseconds, and any other cell, you can refresh them at 256, and then you can have significant power. And actually, ECC have been used, for example, in some works, actually, to add to the ability to detect that. So basically, when ECC detects that there was an error in a particular row, what you do, then you take this row and you put them in the bins of the 64 milliseconds and you remove them for the bin of the 256, for example. This is how ECCs, for example, have been leveraged. Because ECC cannot get rid of that. Because depending on the bit error rate, for example, how much you reduce the voltage, and you basically are not adjusting your timing parameters, the errors can increase. For example, you can start having, for example, let's say 7 or 8, for example, bits per row, and your ECC can completely not help you anymore. But if you do it from time to time and you detect this bit one by one, ECC is still useful to tell you, oh, this row needs to be moved to a low refresh rate.
Okay, thank you.
Yeah.
We have time for another question. No one? Okay, thank you very much, Filipe. Great talk.